All right, so just like in two-space, when we talk about points, one of the things that naturally comes up is determining some kind of formula to determine the distance between 2 points. And we want to be able to do the same thing in three-space. So we're going to assume here that we have these 2 points, just arbitrary points, P1 and P2. The coordinates of those points are x1, y1, z1, x2, y2, z2. In this picture, one of the points was put here, the other one was put here. Now those 2 points determine a box, and this box can collapse down into a 2-dimensional shape if, for example, if these 2 points had the same z coordinate, this top part of the box would collapse down to this bottom part of the box. But the distance formula that we're going to derive here would still work in that case. So we're going to just think of this as a 3-dimensional box. You can see this kind of red pinkish line here joining P1 and P2. If I can find the length of that line, that would represent the distance between those 2 points. And if you notice that line is actually a diagonal for that rectangular solid, that box there. Now, in addition to that, if I were to sort of project that line down onto the bottom surface of that box, you get this dashed line right here, which joins this point to this point opposite that rectangular base. And by doing that, we've actually created 2 different right triangles inside that box. There's this one down here, and you can see the right angle indicated right there. So entirely contained in that bottom face of that rectangle, that box is a right triangle right there. And then the red line itself forms the hypotenuse of a right triangle here. Notice the base of this right triangle goes along the diagonal of that rectangular face on the bottom. So one right triangle here, another right triangle here, and really what we want is the hypotenuse of that second right triangle, because that would be the distance that we're looking for. Okay, so to that end, some of these points have been labeled. This point here is called A, and this one is called B, and so we'll see those show up in this derivation. Let's start with the length of the line segment P1A. Notice that's this line segment right here, P1A. This line segment is parallel to the x-axis, which means as we go from here to here, the only coordinate that changes is the x-coordinate. Notice comparing P1 to A, the y1 and z1 here also appear as y1 and z1 here. So if I'm looking for the length of this leg of that bottom right triangle, all I need to do is determine the change in x going from this point to that point. But we know what this x-coordinate should be. It should be x2, because if you notice, all of the points in this face of this box that's closest to us, if you think of it that way, would all have an x-coordinate of x2, which comes from this point P2 up here. So what we're looking for is the change in x from x1 to x2. That would be the absolute value of the difference between those 2 values. x2 minus x1 in absolute value gives me that length. What about AB? Well, the line segment AB, which forms the another leg of that right triangle down there, that edge of this box is parallel to the y-axis. So from that same logic, the length of this leg of this right triangle is going to be the same as the change in y from point A to point B. You can see from the labels here that's going to be y2 minus y1 in absolute value. Finally, the distance from B to P2, so that's this point to this point. We have an edge joining those points that's parallel to the z-axis. This time I'm looking at the change in z from B to P2. You can see that would be the absolute value of z2 minus z1. And so we have a few lengths here that we can work with. Okay. Now, because we're working with right triangles kind of built into this box here, we can apply the Pythagorean theorem to them. So for example, P1, P2. Remember, that's the length that we're looking for. The length of the line segment P1, P2. It's the hypotenuse of this right triangle here. The legs of that right triangle are P1B, so you're seeing that here, and then B, P2. So this equation is just the Pythagorean theorem applied to those three sides of that right triangle. Similarly here, P1b, which not only is it the leg, one of the legs of this right triangle, it's also the hypotenuse of this bottom right triangle. So being a hypotenuse, it's going to show up on this side of the equation. P1a and AB form the legs of that right triangle. So this equation is the Pythagorean theorem applied to that right triangle. So now notice we have a common side that's showing up in both of these equations. P1b squared is showing up here as well as here. That means I can use the right-hand side of this equation as a substitution up here, giving me this. P1p2 squared equals the sum of the squares of these three sides. However, these three sides are the ones that we found in terms of coordinates up here. So those can be replaced with the sum of the squares of these absolute values here. Now, the absolute value here, what's its job? Well, its job is to take the difference, in this case, x2 minus x1, and if it's positive, it leaves it alone. If it's negative, it takes the opposite and makes it positive. But squaring this value, squaring x2 minus x1, is going to return a positive number regardless. So the absolute values here become unnecessary once we apply that exponent, and that's why they turn into parentheses here. Okay? Finally, P1, P2 squared. P1, P2 is what we wanted, the length of that line segment. So to undo the square, we take square roots of everything. That's where we get our distance formula in 3 space. So here it is again. And I want you to notice the similarity between this distance formula and the one that we use in 2 space. If we're talking about points in 2 space where you only have an x and y coordinate, get rid of the z's, that's what your distance formula would look like. But in 3 space, we have this extra term here. Okay? So let's do an example where we want to find the distance between 2 points. I don't need to graph these points because I have a formula that things get plugged into. Now, if this were a more basic class, I would take the time to show where each number is plugged in and all that. But we have some intuition here and some experience that allows us to make this go a little bit faster. So if I want the distance between these 2 points, let me just call it d for distance in this example. Notice I'm taking the square root of a sum of 3 squares. But the differences that are occurring in each one of these squares is really just the distance between the numbers in my x coordinates, y coordinates, and z coordinates. So for example, from -1 to 0, there's a distance of 1 between those 2 things. So that's going to be 1 squared. From 4 to -3, there's a difference of 7. So that's plus 7 squared. And then finally, from 2 to 5, there's a distance of 3. 5 minus 2, so that becomes plus 3 squared. And I'm fine with you doing this. You don't need to show me the subtraction and all the arithmetic. Go get there a little bit faster. So let's see, this 1 plus 49, which is 50, plus 9, which would be 59. This is root 59. Fairly straightforward, just using a formula. Okay? Now, if you think back to Algebra 2 or Intermediate Algebra, you do a unit in that class on conic sections, and that's where you learn about the formula for, or the equation rather, for a circle. And any intermediate algebra course that talks about the conic sections will start that unit by going over distance formula, because you can take all of those conic sections and define them in terms of distances between specific sets of points. And a circle, by definition, is just the set of all points in 2 space that are equidistant from some given point that we call the center of that circle. So the term distance is important there. A sphere is the 3-dimensional analog of a circle. So how do we define a sphere? Well, specifically, if we're looking at a sphere centered at the point HKL and it has a radius of r, then what we mean by that is that it's the set of all points that are exactly a distance of r from that center point, HKL. But we can use the distance formula to come up with an equation for that. So if the point x, y, z is a point on the sphere, here's the x, y, and the z, then applying my distance formula and squaring both sides of the distance formula to eliminate the radical, I would get this. This is the radius, the distance between any point on the sphere and the center. And notice the coordinates of the center are showing up here, h, k, and l. This should look really, really familiar because it's very similar to the equation of a circle centered at hk. Again, that would be if we just eliminated this last term right there. Okay, the special case where the sphere is centered at the origin is worth noting. In that case, the center is 0, 0, 0, which reduces that to a much simpler looking equation. X squared plus y squared plus z squared equals r squared. Okay, so here, what we want to do in this example is come up with the equation of a sphere satisfying some description. So it says we want to find the equation of a sphere with a diameter having endpoints 1, 4, 2, and 1, negative 3, 0. So let's think about what we need in order to do this. In our equation for a sphere up here, there's two things that you need. You need the center, so we need the coordinates of the center, and we need to know the radius of the circle. Now, thinking about this for a moment, the center of the circle, or the sphere, I should be saying sphere. The center of the sphere, one way of finding that is if you happen to know a diameter. Let's look at a circle for an example. If you have a diameter for a circle, that diameter has to pass through the center, and not only that, the center would be the midpoint of that diameter. It's exactly in the middle. The same thing applies to spheres as well. So if I can find the midpoint of the line segment joining these 2 points here, that'll be the center of my sphere. Now, in the homework, problem number 21 has you coming up with the midpoint formula, but I'm just going to give it to you here. You can derive that in the homework. The midpoint formula, if you have 2 points, x1, y1, z1, x2, y2, z2, is this: x1 plus x2 over 2, y1 plus y2 over 2, z1 plus z2 over 2. And one thing I always run into trouble with in this class, because we use z so often, my z's look like my 2's, so I have to try and distinguish between those. Notice this looks a lot like the midpoint formula in 2 space. Again, you would eliminate the z's and you have the midpoint formula in 2 space. Basically what we're doing though is if you're looking for the midpoint of a line segment with 2 given endpoints, we're just averaging the x, y, and z components respectively. So I'm going to do the same thing here. I want the midpoint of this line segment, this diameter, and that's going to give me my center. So the center is going to be 1 plus 1 over 2, 4 plus negative 3 over 2, so 4 minus 3 over 2, and then 2 plus 0 over 2. Okay, so that would be 1, negative 1/2, 1. That's where the center of this circle should be. Just checking to make sure I didn't make any mistakes there. I think we're good. Next thing I need is the radius. How do we find the radius? Well, there's a couple of ways I could approach it from this point. One, I could find the diameter, the length of my diameter, and then just cut that in half, because the radius of a sphere, just like a circle, is half of the diameter. Alternatively, I have the center right here. I could just find the distance using distance formula from the center of my circle to either of these points here. It should give me the same thing. Because this involves a fraction, I'm going to avoid that, and I'm just going to find the distance between these 2 points and cut that answer in half. Okay, so using my distance formula, the distance, or actually let's not call it d, let's call it r because it's radius, would be the square root of the difference between the x's, y's, and z's all squared respectively. So 1 minus 1 is 0. 0 squared is just that. 4 minus negative 3 is 7, so that's plus 7 squared. And then 2 minus 0 would be 2, so that's plus 2 squared. Now, this is not quite accurate, again, because I'm calling this r, but really this formula here would give me the diameter. It wouldn't give me the radius. So I need to cut that in half or multiply it by 1/2. Okay? Now, this is equal to 1/2 times, what would this be? 49 plus 4. So that would be 53, root 53. But what we really need is r squared, right? So if I want r squared, I'd be squaring both sides of this. This means that r squared is equal to 53 over 4. Don't forget that you're squaring the 1/2. It's not a 2 down here, it's a 4. Putting all this together, the equation for my circle would be x minus my x coordinate for my center, so minus 1 squared, plus y plus 1/2 squared, plus z minus 1 squared. So you're seeing all the coordinates of my center showing up here, equals r squared. We just found that to be 53/4. Okay, there's the equation for my sphere. There's lots of different ways to describe a sphere the way that we did here and ask you to come up with a formula for it. You'll see, or an equation for it. You'll see that in the homework. Okay, one last example before we wrap up section 12.1. This one is straight out of the book, but I like this example. I want to include this, and I also get to use the graphic. It says, what region in R3 is determined by the inequalities shown here? So first of all, this first one might be a little bit difficult until you kind of see what they're going for. It says 1 is less than or equal to x squared plus y squared plus z squared, which is less than or equal to 4. Now, the x squared plus y squared plus z squared shows up here in the equation for a sphere centered at the origin. Okay, so how do we interpret this? Well, if we did x squared plus y squared plus z squared plus y squared plus z squared equals r squared to give us kind of the generic formula or equation for a sphere, then the inequality up there would imply that r squared is between 1 and 4. But that implies that r, our radius, if we take square roots, gives me r between 1 and 2. So basically this is telling me that we're looking at a region consisting of spheres centered at the origin whose radii are any value between 1 and 2 inclusive. Now we also have this second condition here that says z is less than or equal to 0. So what that basically means is we're chopping off the top half of those spheres. We don't want the half of these spheres that have positive z coordinates. So that gives us this region shown here. Notice you have this circle centered at the origin with a radius of 1, and then another one centered at the origin with a radius of 2, and the region between those is part of the region we're talking about, and then those determine this kind of outer and inner hemispheres, kind of forming the boundary of this figure here. So all of the points contained between those form this almost, I guess, like a dome shape with this kind of thickness of 1 unit here. Hopefully that is intuitive, seeing how we could have gotten from here, or gotten to here from this. Especially once we get to chapter 15 and we start looking at double and triple integrals. Inequalities like this are going to show up a lot, so it's something that we definitely want to be comfortable with by the time we get to that point. But that's it for 12.1.